So let's consider the following sort of thought experiment. Suppose I take a proton. Since we can't see electric fields, we need to measure them some other way. And the way we measure them is by looking at what happens to a charged particle. So I take a proton out of my pocket, and I release it at this location. This is going to be what we call the observation location for this experiment. I release it here, and I watch it move, and I discover that it's speeding up. It goes down, and it's speeding up at a rate of 9.8 meters per second every second. Okay. Would you think it's interacting with something? What's it interacting with? It's a gravitational interaction due to the Earth, right? So there was a gravitational field there, we would say, that affected the electron and got it to... Okay, now I go away and I come back at a different time and I release a different proton here at this observation location. And this time I discover that it actually starts to move that way, and it speeds up with it at the rate of 10 to the 11th meters per second per second. Now, it can't do that very long, or it would end up going the speed of light, which it can't do. But initially, anyway, it's got this huge change in its velocity and momentum in that direction. Okay, is it interacting with something? Can this be a gravitational interaction? Why not? Well, okay, so what's your name? Josh. Okay, so Josh says we would notice if there was a massive object that large nearby. It took the entire mass of the Earth to speed this thing up at 9.8 meters per second every second. And if there was something massive enough to speed it up at 10 to the 11th meters per second squared, we would know it was there, because in fact we would also be probably a black hole of some kind. So that's not likely. What kind of an interaction could it be? Could be electric interaction, couldn't it? So the proton was going this way. So what kind of a charged particle could be where that would make it do this? Ah, we get both. Okay, so someone thinks it could be a positive charged particle. Where could that positive charged particle be? Over here, right? What if it was a negative charged particle? It'd have to be over here, wouldn't it? So either way, you could get the same effect. Okay, now you're in a position to make a prediction. Okay, we saw this proton speeding up in this direction. What if I take an electron and I release it at this observation location? What's going to happen to the electron? It's going to accelerate that way, isn't it? And is the rate at which it speeds up going to be the same as the acceleration of the proton? Mass is different. Not the energy is the same. We're guessing the magnitude of the force would probably be the same, aren't we? So it would be speeding up faster because it's smaller mass. Okay, what if I take a neutron and I release it at our observation location? What happens? 9.8 meters per second squared down, right? It doesn't interact electrically. Now, here's what? Yes? Is that neutron given induced charge is not really a very clear term. There's no way that we know of that a particle acquires a charge from some other particle. We'll see later that there are some other things that can happen, but the neutron has a zero charge, and it's going to stay that way. You can't have a charged neutron. Okay? We'll see that sometimes there are neutral things that can be affected by electric fields, but it's a little complicated. A neutron is not one of them. And so it's a good question, but no, the neutron isn't gonna respond to any electric influences. So the question to ask yourself now is, here's the observation location. We've seen a proton, we put it there and accelerated that way. An electron went that way, a neutron didn't do anything. Suppose we don't put anything here. We don't put any particle here. Is there anything at that location? It's the thing that's at the location is what we call an electric field. There is an electric field there, and the way we know, the way we detect it, is by putting a charged particle there and seeing it move. So the electric field is there lying in wait for a charged particle to come along, at which point it'll exert a force on it. So it's almost, if there were a particle there, then there would be a force. And in fact, what you were guessing about the way the forces work is absolutely right, because if we have an electric field at some location, our observation, and it's due to some charged particle whose identity we don't necessarily know. As you pointed out, this field could have been due to a positive charge over there, a negative charge over there, but we'll call it charge 1. So we'll have a subscript 1. Then we observe a force on some particle that we're going to call 2, because this is a different particle. This is the source of the field, and this is the thing that's affected. And in fact, usually when we write an electric field in a physics equation, we actually just leave that part out. But it's always implicit. There's always some location at which we're measuring the electric field. So we always mean the electric field at some observation location. And in fact, you're absolutely right. The force is in fact directly proportional to the electric field, and it's also directly proportional to the charge of the object that's being affected. So a proton experienced a force in that direction. An electron experienced a force equal in magnitude, but in the other direction. Now let's see if this equation works. So this is the thing that's affected, particle 2. Let's see if this equation makes sense in terms of directions. We note that it's a vector equation. This says that electric field is a vector, and what are the units of electric field going to be? What are the units of force? Newtons. And the units of charge in SI units are coulombs. So what are the units of electric field? Newtons per coulomb, right? So newtons per coulomb. Okay, so we put a proton at our observation location, and we saw a force on a proton going that way, right? What do we conclude from this observation about the direction of the electric field at that observation location? Is it the same direction? Do we know anything? Well, it's a proton. We put a proton here, okay? So we put a proton. Look at this vector equation. The charge of a proton is positive. We had a force in the minus x direction. Does the vector equation alone tell you the direction of the electric field? Yeah, it does, doesn't it? Because if two vectors are equal, their directions have to be equal, don't they? And so this is a positive number. That means that we can actually deduce that at this location, there's an electric field in that direction. So the direction of the electric field can be determined by releasing a little positive charge there and seeing which way the force acts on it. And notice we're very careful to put the tail of an electric field vector that we draw at the observation location because that's where we've measured the field, and the field might be different at some other location. So our cue to where we're talking about is where we put the tail of the vector. Now let's think about this equation for a minute and see if you can make the following prediction. If we know the electric field at this location is in this direction, what is going to be the direction of the force on an electron if we put an electron here?